Assalamu alaikum. In this lecture, we are going to discuss about characteristic curves of DC motor. We know that broadly DC motors can be classified into three types: series wound DC motor, shunt wound DC motor, and compound wound DC motor. But we are more interested in learning about characteristic curve of series motor and shunt motor. So in your textbooks, you will find these characteristic curves drawn straight away without any context. These curves are for series wound DC motor, and these are characteristic curves for shunt wound DC motor. So if you look deeper into it, these curves are basically torque versus armature current curve, speed versus armature current curve, and speed versus torque curve. The same thing is available for shunt wound motor, but in your textbooks, the explanations are not quite satisfactory. So I think you deserve to know more about how these curves uh, have come into existence. Since we are all electrical engineering students, we know that if we have a mathematical graph explaining some characteristics, there must be some equations running behind it. So we will try to explain these graphs in terms of equations that we have already learned in our previous lectures. So that will be easier for you to understand as uh, so eventually our target is to make sense of these characteristic curves, right? So there are six different curves. In the next phase of our lecture, we will try to explain these curves using or back using the equations that we have learned so far. And after that, I think you will be able to draw these curves without memorizing these things. Okay, now let's move to the next part of our lecture. Let us begin with the characteristic curve of series motor. And we have seen that there are three characteristic curve of series motor. We are interested in this torque versus armature current curve initially. If you remember, we have already learned an equation about armature torque, which is something like this. Now, if we look deeper into this equation, we will find that there are a few constants already available in this equation. This is like this is a constant, xz is a constant, p by a is a constant. So if we replace all this constant with one constant, so this equation can be rewritten as this font. Also, there is a thing we learned when we were discussing about the classification of motors. We learned that the flux and armature current has a proportional relationship until our motor reaches the saturation point, which basically helps us write this thing in this way. Why? Because flux is proportional to armature current, so flux can be rewritten as armature current here. So in return, we can write that our torque is proportional to the square of armature current. So this thing can again be written as an equation in this form, right? As we know that proportional sign can be removed with a constant. So the final equation that stating relationship between torque and armature current is here, and it is something like this. Now look here, we have a relationship between torque and armature current in form of an equation, and if we can draw this equation in a graph, that will give us the characteristic curve. So if we think armature torque as a variable plotted in y-axis and armature current as a variable plotted in x-axis, so this equation actually tells us that their relationship is similar to a graph like this. I know you all know how to draw this y equals to x square curve, and this is exactly has been done here. Look here, and the torque has been plotted in y-axis and armature current has been plotted in x-axis, and the curve between curve showing the relationship between armature torque and armature current is similar to y equals to x square. So this is the curve, and this is basically the curve of armature torque. And when we were talking about torque associated with DC motor, we learned about another type of torque, that is shaft torque. The shaft torque is related to the output of the motor. So at any instance, suppose we were getting a value of armature torque like this. So at that instance, the shaft torque should have lower value, and the difference between them is the loss incorporated uh, as the rotor starts rotating. So the shaft torque should have a similar curve, but it will be lagging the armature torque. So this is the uh, curve of shaft torque between armature current. Remember, we now there is another thing. We can see there is a straight line. What is that? Okay, so we said that for series motor up to saturation, the flux and armature current has a relationship like this. Now, from as we all are electrical engineering students, we know that if there is some electromagnetism taking place here, that means if some system reaches the saturation, in that case, the flux associated there becomes constant. So once the system has reached its saturation point, so the flux in after that the flux do not have any effect in this equation. So we can ignore this. We can say that at that after saturation, this also becomes a constant. So this goes into the constant value. So at that after saturation, the relationship between torque and armature current is something like this, which is analogous to y equals to kx or y equals to mx. And see, this is the thing available here. So this is the relationship between armature torque and armature current when the system has reached saturation. Uh, when the system was in the process of reaching saturation, this is the curve, and this is the curve for shaft torque between armature current. So now I think whenever you will see this relationship curve or characteristic curve between armature torque and armature current, it will kind of make sense to you why the curve is like this and what is the background mathematics behind this curve. Now let us move to the next characteristic curve, that is speed versus armature current curve. That means to establish this curve, we need to find an equation first where speed of the motor is involved and also armature current is involved. Now to reach to that point, let us begin with this thing. We know that speed of the motor has a relationship with back EMF and flux, and that is something like this. And we also know that back EMF can be written as this thing. If we are talking about series motor, here we are assuming this is the series resistance and armature has some resistance as armature resistance. So again, the back EMF can be written as this also. Now if we go from this to this line, we will see that in the back EMF equation, this P is a constant, Z by A is a constant, and 60 is a constant. And if you replace this constant by a single constant, so this equation becomes uh, simplified, and this is the version of it. And from here, if we equate for speed of the motor, we get an equation like this. Okay. So in this equation, we will fill the value of back EMF from this. As back EMF is equals to this, we will feed the value of back EMF here, and this is what the equation will look like. And if we do further calculation, we reach to a point where we get the relationship between speed of the motor and armature current in this format. Here the V value, the applied voltage itself, it is also a constant. The K2 here is a constant and K3 here is a constant. So the only variables that we are interested in are the speed of the motor and armature current. So they are basically forming an equation like this. If we plot the speed of the motor in y-axis, we can replace the speed of the motor as y, and if we are plotting the armature current in x-axis, so this is coming as something like this, or we can rewrite it as xy equals to k. I Hope you all know how this mathematical equation is plotted in graph. This is obviously a graph of a hyperbola. So if you plot the speed of the motor and armature current in a graph, this should look like this. If we go at the first point, see here, this is the graph we have reached after doing our mathematical calculation. Now let's move to the another characteristic curve of series DC motor, that is speed versus torque curve. In order to have a characteristic curve of speed versus torque, we need to establish an equation where speed of the motor and torque is involved. So we will carry from the we will carry from the equation we solved for our last characteristic curve. So that is the equation here. We know that there is a relationship between the armature torque and armature current, and that is this thing. So we can equate armature current like this. So now if we plug the value of armature current here, so this will give us this equation like this. Okay, and this is also giving us uh, an equation of this order, where we can see the interested variable, the speed of the motor and the armature torque. Now if we are plotting the value of the speed of the DC motor in y-axis, let us label it as y, and if we are plotting the value of the armature torque in x-axis, so this will be something like this. And if we equate it, we're basically getting an equation of this order. So this is also a graph of a hyperbola, which is similar to the graph we drew previously. And if we plot the speed of the motor in y-axis and the torque at y-axis, we get a similar curve, but the difference here is that this curve will be much steeper than the previous one, as we have a square attached to our y-axis variable. So that is the key differences in terms of graphical representation between this speed versus torque curve and the speed versus armature current curve. Though it is not properly visible in your graph given in the textbooks, but I believe now you all know there are some differences between these two graphs, and you know how they have come into existence. You know the background mathematics uh, leading to these graphs. So next we will see the characteristic curves for our shunt motor. For DC shunt motor, we have those three characteristic curves that we have already seen for series uh, motor. As we started with the torque versus armature current curve for series motor, we will begin with the torque versus armature current curve for shunt motor here also. Okay. Previously, we have seen that we have a equation for armature torque, which is which we have something like this, and for series motor, we didn't consider flux as a constant, but here we will consider flux as a constant, because if you remember when we were discussing about the classification of DC motors, we clearly stated that the flux that is responsible for the rotating of the motor in shunt wound motor is coming from this particular winding, and this is a fixed winding, and the flux that is being generated here is also fixed, which means this is also a constant quantity. So when we were explaining the equation for armature torque for series motor, the scenario was different, but when we are discussing the we are analyzing the equation of armature torque for shunt motor, the scenario is different, because this is a constant value, flux is a constant here, z is a constant, p by a is constant, so which leaves us with only variable ia. So the relationship between torque and armature current for shunt motor is a simple relationship, that is something like this. And if we are plotting this variable in y-axis and this variable in x-axis, That gives us a graph like y equals to kx, or you can say that y equals to mx. So this is the characteristic curve for curve of torque versus armature current for shunt motor. Let us double check it from the graphs shown in your textbook. See, this is the graph. And as we did for the shaft torque for series motor, we will do the same thing for shunt motor here. So the shaft torque will lag the armature torque. So this is the shaft torque relationship with armature current. Now let's move to the next relationship or characteristic curve, that is speed versus armature current curve for shunt motor. So the beginning of the explanation is like the same. We know that back EMF can be written as this format, but the thing is flux is a constant quantity for shunt wound motor. So this is a constant, Z is a constant, 60 itself is a constant, Py is a constant. So after removing all the constants, we are left with only this thing. So back EMF for shunt motor can be written as this. Again, we know that back EMF can be written as V minus IARA. Right here, there are no other resistance involved here. So if we equate our equation for speed of the motor and for armature current, we get something like this, and V is a constant here. So this whole thing is a constant, and this part is a constant quantity also. So if we are plotting n in y-axis, and let's say we are converting this as a bigger constant, let's say we are naming it q, and this as p, and this as x. So this our characteristic curve should be something like this: y equals to q minus px, which means this will be straight line which has a negative slope. That means it should be something like this in this order, and it has a constant that is positive. So this is how our characteristic curve of speed versus armature current should look like for shunt motor. Let us verify whether we have reached to the correct curve or not. Yes, we have reached to the correct curve using our mathematical knowledge. Okay, now let's move to this characteristic curve of speed versus torque. So we need to establish a formula for speed versus torque in terms of shunt wound motor. We will begin with the formula of the last characteristic curve, which was speed versus armature torque, and we know that there is a relationship between armature current and armature torque, and flux is a constant quantity in terms of shunt motor. So the relationship between them has no flux involved here. So this is a linear relationship like a straight lines equation. So we can replace this I1 with this equation. So that will give us a similar equation, as we can see. If we plot n in y-axis and torque in x-axis, so this is all the same. Let's say we are putting it a bigger k minus mx. So the relationship between the speed of the motor and the armature torque holds similar kind of characteristic curve. So this will be a straight line having negative slope and constant with positive value. So this should be the uh, figure of the characteristic curve between speed and torque of shunt wound motor. Let us again verify whether we have reached to a correct curve or not. Yes, we have done it correctly. So that was the characteristic curve or the discussion about characteristic curves of DC motor. We have discussed it for series wound motor and shunt wound motor. And that was it from my side for this lecture. I hope it helped you learn these topics uh, a bit easier way. That was it from my side. Thank you very much.